Welcome, guys, to this wonderful course. Uh, Today, I want to look at introduction to interpolation, right? So what is interpolation? So, interpolation was first used long time ago to estimate some of the values that were missing on some statistical or function tables. For example, if you look at the table on your right there, you will see that for values of x, you have got 0, 1.0.1, 0.2, 0.3, 0.4, and their respective sign of x values or corresponding values. How about if you want the value of 0.15, which is not in the table? Then that's where the concept of interpolation was introduced to approximate or to estimate values that are not obvious or that were not in their statistical tables, since these guys, the ancient guys, did not have the internet and the calculators to calculate complex functions. So they would use these techniques to interpolate and get an approximate value. As you can see, the linear interpolation for sine zero point 0.5 is so close to the actual true value, which is of sine 4.5, as you can see there. So interpolation is also another powerful tool to estimate data or to predict missing data. Usually, I use this to predict missing data. For example, let me give you another example. During COVID, you find that during COVID, were COVID lockdowns, people were sent home. You find that a data collection station sends quite a number of people home, and then you get maybe 2 or 3 days of missing data. You can use interpolation to estimate that data set which is missing. So that's one of the power of using this method, interpolation. All right, so the difference between interpolation and these other methods, like the ones that we have covered, the neutron rason, the bisections, those are like the estimation, those are like estimating points. So they estimate, whereas interpolation deals with finding the points within our data set or in an interval between our data set. Those ones were dealing with finding the next point. So that's the difference. So let's look at an example. So suppose you have got an experiment of viscosity of water as a function of temperature. You have got that table and you want to estimate the viscosity when the temperature is 8 degrees. From our table, we don't have an 8 there, but it's in between 5 and 10. So to do that, we will use a polynomial to fit the data set. So remember the curve fitting that we did in part one. We would want to fit that curve using the given data set on the previous slide. That will give us a linear fit, will give us a line of this form, and then we can use this line to approximate for t is equals to 8. So that's the concept that we want to use this method. So the existence and uniqueness. So there is a theorem that states that there is a unique polynomial of order n less than or equal to n such that f of n is equals to f of f of n is equals to f of x for n 0 up to n, for I 0 up to n. So there is always a unique function that can be used to approximate values or to interpolate values. That's what the theorem is stating. All right, so examples of polynomials. So we can have a linear polynomial like this. So if you have got your data points, you can fit a line. If those points fall in a line, or if you have got your data set like this, you can clearly see this is not a line, can fit a curve, and this is of order 2 or more. And for order 1, or can fit a line. And then linear interpolation, you should be given 2 points. 2 points, this is x, this is y at x naught, or f of x at s naught, this is x1, and then this is f of x1. So you are given 2 points there. Then you use those 2 points, using those 2 points to find f of f1. So this will be equal to f of f1, where plus, you recall that this is the gradient of the line. So this is the gradient of the line, and then x minus x naught, and this is your y. So technically, you are using the equation of a line where the gradient of a line is given by f of x1 minus x naught over x1 minus x naught. So the first polynomial that interpolates 1, 2, and 2, 4. So if you are given these 2 points, the first polynomial that interpolate these 2 points will be f of x naught. X naught will be 2. This is 2. F of x naught. So we substitute, this will be 2. F of x1. This will be 4. F of x naught is 2, and then x2 is x1, sorry, is 2, and then x naught is 1, and then x naught is 1. Solve this, should be able to get the polynomial 2x. With interpolation, there is no need to cram these formulas, but make sure you master how we are going to apply them. Make sure you master the steps. It's easy when you master these steps than when you memorize the formula. And then for quadratic interpolation, you have got 3 points that you are given, and then you get your polynomial in the form b plus b1 x minus x naught, b2 x minus x naught, x minus x1, where b naught is f of x naught, and then b1 is your gradient. b1 is your gradient evaluated there, and then b2 is the difference between the gradient at these 2 points. So you have got the difference between the gradient x1 x naught and x2 x1. So that's the difference of those. So in general you get the n plus 1 points given by this, and the polynomial to that will be given by this. As you can see, the polynomials will be increasing order there, where b1 is the gradient of f of x, b1 is the gradient of f of x. So technically these are gradients. The b's are slopes or gradients. Then we've got the divided difference. The divided difference method, we have got f of xk being f of xk. This is the 0th order divided difference. And then this one, when you're finding the gradient of the difference, this is the first order. This one, when you're using x1, x2, x3, this is second order, computing the gradient of that, and so on. All right, so this is the divided difference table. Here you will have your x, x1, x0, x1, x2, x3, and then these are your values of f. And then this f of x0, x0, so this is the gradient between these 2 points. Then this is the gradient between x1 and x2. And this is the gradient between x2 and x3. This is the gradient using x1, x2, and x between x1, x2, and x2. x1, x2. This is the gradient between x1, x2, and x3. This is the gradient with respect to x1, x2, x3, x1, x0, x1, x2, and x3. The formula for the polynomial will be given by the summation of I from 0 to n of f from x0 up to xi times. This symbol means that we are multiplying all these x minus xj there. All right, so I think this discourse will be clear when we look at the following example. So take note, if you are given a table on your right, x, 0, 1, and minus 1, corresponding with minus 5, minus 3, and minus 15, you can write that those entries as columns in your divided difference table like that. So the first data set will give you entries of these two columns. Take note of that. All right, so the first two columns of the table are your data columns. Take note of that. And then the third order difference. The third order difference, this one is your gradient with respect to your data sets. And then the fourth column is the second order difference. It's a second order difference, which is the gradient using this column and the first column. Okay, let me show you how you compute these values. All right, so now that you know where the first two columns came from, you can then try to estimate the first divided difference column and the second divided. And so for us to compute the value that goes into this box, this will be the gradient. So you check here where we have got this red mark, check do the gradient, compute the gradient of this using this. So the gradient is change in y over change in x. So this would be minus 3 minus 5 over 1 minus 0. So this will give us a 2. And then for this 6, you are using this block, compute the gradient again. So this is minus 15 minus 3 over minus 1 minus 1. This will give us 6. So this is 6. That's where that 6 is coming from. Then when it comes to the 4, it's interesting how we compute 4. So another gradient, but for 4, we still make use of these 2 points. So this is 6
minus 6 minus 2, which is 6 minus 2, 4, and then divided by minus 1 minus 1 minus 0, which gives us 4. Right, so for the values that are in this first gradient, first divided difference method, you take, you let me, for these values for 2 and 6, you are using your denominator without skipping boxes. For example, these are concurrent points. And then for values in this next column, for values in this column, the second divided difference, you skip 1. So for example, this one minus 4, you take 0 and then you skip 1 and then you take minus 4 as your denominator. Suppose we had another column here, you will skip 2. Take this one, skip this one as well, and take the third one. Okay. Alright, so your divided difference table will be complete like that. Then from there, you can write down your polynomial. So your polynomial will be a second order divided difference polynomial, which is given by f of x, which is minus 5, and then plus 2 bracket x minus the first one 0 minus 0 minus, take the second one, which is minus 4, this one minus 4, and then this will be x minus 0 times x minus 1. So that's your divided difference formula. All right, so let's look at these two examples. So looking at these two examples, what do you observe? So you should observe something. You should observe that these two columns and rows are the same, except that the order there is different. The order is different. Here for 1, 2, 3. Here for 2, 1, 3. But everything else is the same. All right. So the divided difference tables for those and polynomials for those two tables is the same, as you can see from there, and this should show you that ordering the points should not affect the interpolating polynomial. So if you're ordering different points, this should not affect your polynomial. Maybe let me do this one again, this table again. For you to get this 3, it will be 3 minus 0, which is 3. It's because you are computing the gradient using this 4. So 3 minus 0 is 3. 2 minus 1 is 1. So 3 divided by 1 is what? It's 3. And then this one, we are using these 4 boxes. 8 minus 3. 8 minus 3, that's 5. 3 minus 2, that's 1. 5 divided by 1, it's 5. That's good. And then for this one, it's 5 minus 3, which is 2. And then now that we are on the second, we need to skip this box. We need to skip one box there. So we need to skip this one for x for the denominator. We skip this one. So for the denominator, it will be 3 minus 1, which is 2. So 5 minus 3, 5 minus 3, 2. 3 minus 1, which is 3 minus 1, which is 2. So 2 divided by 2, you will get your 1. So you do the same thing there to get that table there. Fine. And then your polynomial will be this first row, excluding the x value. So it will be this 0 plus 3 x minus 1 first point plus 1 x minus 1 x minus 2, these first 2 points. All right, so here is a more interesting example. Right, so I'll just run through this example, but make sure you do this practice and work out this example. So you want given this function and you want to interpolate the data set and come up with the interpolation polynomial. So the data set will give you your first two columns. So your data set will give you your first two columns. And for this column, you're simply computing a respective gradients. So this one, this 4, 9 minus 6, 3 divided by 7 minus 6, 1. So this is 3. 6 minus 1. So this one for 5, this one. 6 minus 1, 6 minus 1, 5. 6 minus 5, 1. So this is 5. Then this one, 1 minus 5 minus 4, 5 minus 4, 1. So minus 4. 5 minus 3, 2. 4 minus 2, 2. So divide 2 by 2. This is 1. For this one, this one, so this one will be 3 minus 5. 3 minus 5. This will be minus 2. And then remember, we are now on the second. So if we are now on the second, it means that we are skipping 1 point on our denominator. So this is 3 minus this, 3 minus 5. This will give you minus 2. And then we skip this one. So this will be 7 minus 5, which gives us 2. So this is minus 2 divided by 2, which gives us minus 1. And then for this one again, it will be 5 minus 5 minus 4, which is 5 plus 4, which is 9. And then remember, we skip 1, skip this one. So this will be for this one. So this will be 6 minus 4, 6 minus 4, which is equals to 2. So 9 divided by 2, that's 4.5. So you continue again and satisfy yourself that for this one, you get that one. You can pause the video and compute the gradient for this one. Again, if you want to compute for this one, this value there, you will say minus 1 minus 4.5. So that will give you minus 4.5 minus 5.5, sorry, because this is minus 1 minus 4.5. So this is minus 5.5. Minus 5.5. Remember, we are now on the third divided difference. So we skip 2 boxes now on the denominator for the gradient. So we skip 2. So this will be 7 divided 7 minus 4. That's 3. So 5.5 minus 5.5 divided by 3, that should give you minus 1.833. And then for this one, so you can pause the video and compute this one again. So this one, you'll skip these two, for the denominator, whereas your y is, will be this one for the gradient. And then for this one, you will use minus 1.833 minus 1.5, and then you divide by Now we are skipping 3 digits there. Then divide by 7. Divide by 7 minus 3. As I'm talking like this, you can pause the video and do those computation and satisfy yourself that you get those. Sorry for that. So as I'm doing this, you can pause the video and make sure you compute those values or those gradients. So that's it. And then when you obtain all those values there, those are the values that you need to come up with a polynomial. So your polynomial will look like this because this is a fourth order. So this will be 3 plus 1 times x minus the first point there is 2, and then 1 minus 1.667 x minus 2 x minus 4. So this is 2 plus 1.417 x minus 2 x minus 4 x minus 5 and minus 6750 x minus 2 x minus 4 x minus 5 x minus 6. So in summary, interpolating condition, you should know that f of xi is equals to f of n xi for n0, 1 up to n, and that the interpolating polynomial is unique. The different methods can be used to obtain is the Newton divided difference, and then we have got the Lagrange interpolation and other methods. So in our next lecture, I'll show you how you perform the Lagrange method. So in this lecture, we're just doing the Newton divide difference method, which was only centered on finding the gradients, and then from there you come up with your polynomial interpolating. So thank you.